Okay, so today we are going to look at the last machine learning model that we have in this unit before we cover deep learning and the hyperparameter tuning part. So today we are going to look at the XGBoost model. Let me zoom in a little bit so that you can see what we have here. I've also shared this notebook link to you so you can see what I have over here. Let me see the share part if you have access to what I'm showing you here. Yeah, so you have access. Let me also share the same in the chat. Then you can have a look at what I'm looking at. Okay, so today we are going to look at the XGBoost model. And the XGBoost is an advancement of the random forest and the decision tree based model. So it is one of the best models that is used out here for machine learning competition and for creating the creation of machine learning models. And well, when we look at this content, you'll get to see why it's one of the best. Okay, so XGBoost is one of the most popular machine learning algorithm these days. So regardless the type of prediction task at hand, regression or classification. So XGBoost can handle both regression and classification tasks as a single model. So you can use it to fit classification models, and you can also use the same model to fit regression based models. So XGBoost is well known to provide better solutions than other machine learning algorithms. So in fact, since its inception, it has become the state-of-the-art machine learning algorithm to deal with structured data. So the reason as to why we are using Colab today is because I believe XGBoost has not been installed in your system. And if you want to install it, you'll have to run pip install XGBoost. So what makes XGBoost so popular? So its speed and performance. So what you need to note is that Python is not one of the fastest language out here, but we have other languages which are fast in doing their computation. So originally XGBoost was written in C++. So it is comparatively faster than other ensemble classifiers. Okay, so ensemble classifiers are those models that group together other models. So for example, you might take 10 decision trees, group them together and come up with an average score. So that's what ensembling means. Then we have core algorithm is parallelizable. So here we can use GPUs. Okay. So because the core XGBoost algorithm is parallelized, it can harness the power of multi-core computers. So it is also parallelizable into GPUs and across networks of computers, making it feasible to train on very large datasets. So for our models, we have been using the CPU mostly to fit for power. So here, if we check performance on my PC, you can see mainly I'm using the CPU to like do the model fitting. So the CPU is at, maybe for example here you can see it's at 41% utilization, but the GPU is at 7% utilization. So if I wanted to like feed models faster, I will switch to my GPU and feed them faster. And we also have that option on Colab here. So I can click on runtime, then I can change runtime type, then I can add a hardware accelerator. So you can see here they are called hardware accelerator, which means that when you feed these models, the process will be even more fast. So here you can click on GPU, then save, but I won't do that for today. So we have GPU. Yeah. Then the other thing is consistency outperforms other algorithmic methods. Okay, so it has shown better performance on a variety of machine learning benchmark datasets. So if we go to the UCI library, so any dataset that is here, the XGBoost model has given us the best performance for the majority of the datasets that are here. Okay. Then the last thing is wide variety of tuning parameters. So we will see some of the parameters that we can tune for XGBoost, and this allows us to modify the model and make the performance be even more better. Okay. So that's the advantage of using XGBoost. So from the name XGBoost, why don't we discuss the meaning of boosting? So boosting is a sequential technique which works on the principle of an ensemble. So we can look at this diagram here. Then we have box 1. So you can see in box 1, we have the plus signs and the minus signs. Okay. So what a boosting model will do is, first of all, it will, so this is a classification task, let's say, for example. So what a boosting model will do is, first of all, it will feed the first model, and the first model will identify one class that is fully isolated from the other classes. So here you can see these two plus signs are in their own unique part, whereby we can draw this boundary line called D1. And over at this other side, on the right hand side, we have the plus and minus mixture. Then what we will do next is we will create box 2. So this is our, let's say, model number 2. And model number 2 will capture all the other plus signs that we've left out. But in this case also, create a boundary where we have only the minus signs. So here you can see we have the minus signs. Okay. Then we have box 3. So what box 3 will do is it will try capture all the other minus signs. So these other signs here. And then these three boxes will be combined to come up with this last box, which is box number 4, which has 1, 2, 3, three boundaries where we have the minus signs in their own location or in their own small boxes, and the plus signs in their own other small boxes. Yeah, so we can see what we have here. So box 1, the first classifier, creates a vertical line split at D1. So it creates a vertical line split at D1. It says anything on the left of D1 is positive and anything on the right of D1 is negative. However, this classifier misclassifies 3 points, okay? Then box 2, so this second box here, it does the opposite. So it does the opposite of box 1. Then box 3, again, the third classifier gives more weight to the 3 misclassified points and creates a horizontal line at D3. So this is the horizontal line at D3. Still, this classifier fails to classify the points in the circles correctly. So box 4, this is the weighted combination of the weak classifiers. As you can see, it does a great job at classifying all the points correctly. So remember when we were dealing with random forest, so the approach was kind of similar, but the random forest model was taking into account different decision trees, but not working with such kind of boxes. Okay. So the basic idea behind boosting is this. So it combines weak learners and comes up with a big, a
Just
bigger model.
a
Yes, yes,
question. So
yeah,
this box 4, the way
yes,
they've classified,
yes,
like the first two pluses on the left, so
yeah,
that's one classification.
yeah. That's
Yeah.
one
Then the
classification.
top plus the top three pluses, that's another one.
Yes,
Then the three minuses, the one in the middle, that's another third class.
yeah.
Or and the two minuses on the right, because I'm saying that they're like separate. They're separated.
So see this first model, we have the pluses which have been highlighted, right?
Yeah.
Then for the second model, we have the minuses which have been put into like a separate box on their own, where they are having the red part, right?
Yes.
So here you can see any part that is blue means we have a plus, and any part that is red means we have a minus. And the last model takes into account all these other minuses. And when we combine them, you can see we will say that the green parts should be plus and the red parts should be minuses. Yeah.
Okay. So would you say then in box 4,
Yes.
they're being classified into two classifications, the
Yeah,
blues
box
and the
4 has
reds?
been classified into two classifications, blues and reds.
Red.
Yeah.
Yes. Okay. Okay.
Yeah, yeah, that's it. And you can see it's a combination of all these three boxes that we have up here. Yeah. Okay, let's proceed. So let's have a look at how Xgboost works. So today I have some code already written for you, but we will discuss them in detail. So here we are getting data sets from sklearn. So anyone else with a question? Yes, Chacha.
Yes, Joseph,
Yes.
kindly go back to the other four classes.
Yeah, there is one here.
Yeah.
Okay.
So there is a part I didn't get,
Yeah.
especially on the sorry, on the one that the box
Yes.
the two class, the box one and box two
Yes.
classes.
Yes.
Yes, that's where I didn't get it properly,
Okay.
and especially on the minuses and the positives.
Okay, I can draw this for you and explain then.
Awesome.
Yeah. So, for example, let's say we have these diagram that we are trying to classify. So here we have points 0, 0, 0, then let's say 0 again, then we have minus, 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 then 0, then 0. So something like that. So this is our data, how it looks like maybe when it's plotted. So what we will do is we will feed model number 1, so which is a weak model. So for model number 1, this is what we will have. So model number 1 will say like, let's classify these 3 points that we have over here first and say that these are the classifications that we need, right? And then for the other points, we won't capture them. So that's model number 1. Then we have model number 2. Model number 2 will capture maybe the top 3. So we will have something like this. So this model says that I can classify these top 3 well, but I can ignore all these other ones, okay? Then we can have model number 4. Okay, so not model number 4, but model 3. So model 3 will say something like, I can classify this last point here and say that this is class 0 and ignore all the other ones, okay? Then we can have model number 4. So model 4, let's say it will capture maybe these negative points that we have here. So it will say something like this part here, this part down here can be the part where we have our minus signs, okay? So all these 4 models that we have here are right, but they have one weakness. So these points, the minus signs, so I can say they have not been well classified for us to like say that the minus signs are here where they are and the zeros are all here where we have them. So what we will do is we will create our fifth model. So model number 5, which is a combination of all these 4 models. And this is what we will have. So first of all, you should note that model 1, 2, 3, and model 1, 2, and 3 have unique values. So we don't have a mixture of values. So our model will consider those 3 models first as compared to this last model that we have over here. So we will have this. So we will have this first line. Then we will have this second line. So this is from model number 1. This is from model number 2. So this is from model number 1. This is from model number 2. And this is from model number 3. Okay. So these ones we can say they are, so let me change the color. So we can say these, let these be blue. Okay. So those points are blue. Okay. Sorry for that. Then these points will be for our zeros. Sorry for that. Okay, so these will be our zeros. And then the remaining part will
Just
be
get
our
some water.
minus part.
It'll be
Okay.
okay.
Okay, thank you. I'll get some water. So this remaining part here will be our minuses. So do you see how an XGBoost model works? It simply works that way. Do you now understand how it works?
So, Joseph,
Yes.
so when you're trying to explain boosting, so it's boosting from the first data box, or what's the word boosting here? Is it like the way we understand how to boost something, or?
So it's like taking the first correct model that, so we can say that this model is 100% at predicting this part that has been highlighted, right? For model 1. And for model 2, it's 100% accurate at predicting this part here. So what boosting means is we are taking a collection of 100% weak learners and combining them to come up with an 100% more capable model where it can capture the majority parts of the data. Yeah, so that's
Okay.
basically what I mean.
So it's boosting from each week model, like 1, 2, 3, 4, 5, each 100% week model,
Yeah,
to boost it into one whole combined model, model
yeah.
5 that
So
is now.
we
Oh,
can say
okay.
something like this is our 10% model, right? This
Mhm.
is our other 10% model. This is our other 10%. And this is our other 10%. So it's combining all these and coming up with something that is 40%, let's say, more powerful.
Mm,
Yeah.
okay. So even the negative parts is still it's one whole combined model.
Yeah, it's one whole
Okay.
combined model.
Okay.
Yeah. So do you understand the boosting part? Yes. Someone raised his hand. Oh,
It's me.
okay. Yes.
So, Joseph,
Yes.
let me try to bring kind of an example
Yes.
of the, let me say, the lending company
Yes.
or the loan company.
Yes.
Let me say the loan status
Yes.
projected at
Sorry, Chacha, I think your microphone is not so clear.
my mic
There's
is not.
some noise.
I'm okay now.
Yeah,
Yeah.
that's better. Yeah.
Awesome, thank you. So, let me try to ask
Mm-hmm.
now. Is it like, for example, where you have customers from a given region
Yes.
as much as they have the other negative features,
Yes.
but their loans will be accepted. Customers from a given place have
Yes.
negative features, but
Yes.
from the previous history,
Yeah.
their loans have been accepted because of their previous history on paying back the loan. Or how does it work? I try to give that as an example just to try to understand, like, if this part of the model is
Yes.
accepted, this part of the model is accepted, this other part of the model is accepted, but when you combine all the four models, you have one model that is accepting all other, let me say, features that are acceptable as per any organization. So in this case, does it mean that you have to personally, in your mind, that is, pick the positive ones that you feel are okay, or it will be automatically picked? Yes,
So I
yes,
think
Walter.
it will automatically pick. Yeah. And when fitting models, I can say maybe like, so when fitting models, I can say you can consider such things like, well, let's say when the data is different. So let's say people from different region usually pay different amounts. So while working on the industry, so I've worked on such kind of projects whereby different locations have different payment rates. So what you will be required to do is create different models. You can't like create a single model and expect it to cover like or expect it to learn like the differences that we have in between those regions. So you at the back of your mind you have to consider that. So you need to monitor the so that and that's the basically the use of EDA. So for while using EDA, you can compare the different regions and see the different performances that we have. And when you get to the model fitting part, you can see if you can come up with an average model whereby you can compare the performance of the model on the different regions and see if the performances are different. And if they are not different, then you can combine them. But I will suggest that you create a model for each region, right? But not for each region, but for different countries. That will be it. Because region wise, let's say, for example, in Kenya, we have lots of regions, and creating a model for each region will be tiresome. And I think the performance should mainly be based on a country and not a region because the so things like let's say CPI, the consumer price index, are what show are things that we use to monitor the performance of a country's currency. So for example, things like the employment rates, the GDP, so things like that. So you will notice that the GDP for a given country is different than one from another country. So you cannot like split the data region wise, but you can split it country wise. And for model creation part, I think it can it can note the different performances that we have in different regions, and it will add more weight to that region, and that's the reason as to why we have hyperparameters, and the reason as to why we have these tree here. Okay. And so I can summarize this and say that one, so the model itself can handle the differences that we have in different regions. And two, this will be based on what kind of data you are looking at. And number 3, I can say, is according to your EDA results, you should be the one to decide if you should create different models or if you should come up with a single model. Yep. Has your question been answered?
I'm good.
Okay. Yeah. I hope we can proceed on now if you don't have any other questions. Okay, I guess we can proceed. So here we have the California housing dataset. So it's somehow similar to the housing dataset that we used in class for our illustration. So we import the dataset, so using the fetch. Okay. So from sklearn.dataset, import fetch California housing. So we import it and store it in a variable called housing. And remember that what I said is this data is stored in terms of a bunch. So a bunch is similar to a dictionary. And inside here, we have the data itself, we have the target variable, we have the frame. So we have the target names, we have the feature names, and we have the description of the data set. So we import pandas and convert the data from being a dictionary value to being a data frame. And we set the column to be equal to the feature names here. And that's what we have. So here we have the median income, we have the house age, we have the average number of rooms, average bedroom, the population, the average occupancy, latitude and longitude. So this is the location of that house. Okay. Then after that, we add the target column, so which is the price. So our end goal will be to predict the price of a house given its features. Okay. So here we check the data info. You can see we have no null values and we have 20,640 observations for each and every column that we have here. We can have some summary statistics, so you can go through that when reviewing what we've done today. Then here we create our Xgboost model. So we will have from import Xgboost as XGB. Note that we are not importing Xgboost from sklearn, but it's a library on its own. Okay. Then we import the mean squared error as our metric. So import pandas, then we can have import pandas as PD. This is unnecessary because we've already done that. So next we set our X and Y. So our X is all the features that we have here apart from price. And our target is price. Yes.
Yes, Joseph, let me try to understand this.
Yes.
Sorry, let me bring my mouthpiece closer. Um, in this, the moment you're importing the XGBoost
Yes.
and the other libraries,
Yes.
does it mean that we have already understood
Yeah.
that the kind of model that we're trying to use, for example, the one we were trying to use on the
Hello,
RTA
I can't hear you well.
dataset? Oh, you can't hear me?
Yes, we have some
Am I good
buzz
now?
inside. Yeah, a little bit better.
I think I have to change my machine, but
Yes.
does it mean that
Yes.
this comes after you
Yes.
have analyzed all the models that you're supposed to use and you have realized that the accuracy in them is lower than the one that is expected? Or does it come in when you suspect that the model that you're trying to use won't cover? Like, for example, yesterday
Yes.
we used the not yesterday sorry
I think on Tuesday.
on Tuesday
Yes.
we used the random forest
Yes.
and the logistic regression,
Yes.
and we realized they are both working well, right?
Yes. Yes.
And those ones, for example, in those ones, do you
Yes.
think it was necessary to use the Xgboost, or is it always coming up after you have tried your models and you have realized that all these models are not working well as I expect? So I think I need to use this. That is my challenge now.
So I can explain that. So when fitting machine learning models, and I guess I was to explain that maybe later on. So the first thing you need to do is fit a base model. Okay. And what does a base model do? So you will use this model to compare its performance with all the other models. Okay. So we compare the performance of the base model with all other models. So what we check is the base model overfitting or underfitting. So things like that. And once you've created your best model, so you go ahead and fit other models. So after you've fitted your other models, what you do is you compare. Okay, so not compare, but what you do is you get the model, with the highest accuracy. Then you conclude and say that this is my model. So do you get that? So this is the process you follow on a real world data set. So you fit a base model. So your base model could be your linear regression model. Then you go ahead and fit other models. So for example, the random forest, the decision tree, the XGBoost, then the neural networks. So after fitting all of them, you compare and see which model in here has a higher performance than this, and which model in here has a higher performance than all of them in here. Then you conclude and pick that model. Hope that answers your question. Yes.
Joseph, good evening.
Good evening.
Now, there was this class that we ran around 4 models that are using the def function,
Yes.
and I think Chacha mentioned it yesterday that
Yes.
we found that most of the models were not performing well.
Yes.
So, what you just talked about right now,
Yeah.
that we when we have a data,
Yes.
we, it's important to run all the models.
Yes.
Then from there we can get the best one, the best model that performs well.
Yep.
So does it mean that the one that how we use the def function, is it the ideal one to the run the models at the same time, or one is allowed to do a model at a go, then goes to another one like that?
One is allowed to do one individually, so it's not a must you feed them all at once. So you
Okay.
can fit a logistic regression on its own, you can fit a linear regression on its own, as long as you have something that you can show. And in this notebook, I've done that, so you'll get to see what I've done.
Okay.
Yeah. Okay. So yeah, let's proceed. Then you'll get to see what I've done in this notebook. So here we are fitting an XGB model. So what we do is we create our X and Y. Then after that, what we do next is we create a data matrix. So this is new. So Xgboost has something known as a data matrix. And what is the use of a data matrix? So it improves the performance of the model, as you can see here. So this is how you create your data matrix. So you create a variable, so called maybe data underscore d matrix. Then you say let that be equal to xgb dot d matrix. Then you should specify your data in your label, and you should have your data matrix. But it's not a must you use this, so you can just use your x and y as they are. Then here we can discuss some of the hyperparameters that we have for XGBoost. So at this point, before building the model, you should be aware of the tuning parameters that XGBoost provides. So, well, there are many of them, and the common ones are here. So for example, we have the learning rate. So this is the step size shrinkage used to prevent overfitting. So, and it ranges from 0 to 1. Then we have max depth. So determines how deeply each tree is allowed to grow during any boosting round. Then we have subsample, percentage of samples used per tree. But I guess this part is not that much essential because you can go ahead and fit your model without using the hyperparameters, but you just need to know them by the name. Then the hyperparameter tuning part will help you, because knowing what each hyperparameter means won't help you, but the results are our main key point. But the main hyperparameter you need to learn about here is the objective. So determines the loss function to be used, like reg linear is for regression problems. So if you are fitting an XGBoost model to solve a linear regression problem, you should use reg linear as your hyperparameter. When you are using when you are trying to solve a classification problem, you should use reg logistic. So this is the only important hyperparameter you need to know. Okay, so here we split our data into training and test set. So I've been showing you this. Then
Just
yes,
I'm sorry.
it's okay.
I might be actually taking us, kind of slowing us
No, it's
down.
okay, it's okay, it's okay.
But do you remember in the last on Monday we
Yes,
used the N estimators?
the number of estimators, the number
Exactly.
of trees you want to build.
Absolutely yes.
Yeah,
But in that case, before that, we had never learned about that, right?
yeah, you've never learned about that.
But we learned it on Monday, and it wasn't explained what
Yeah,
it meant.
yeah,
So for me, I find it a little bit
confusing.
hard actually
Yeah, yeah,
to say that we'll, kind of, in this case, like, when we say in this case, it is in this kind of data we're using, we're going to know that one.
yeah,
But it hasn't been explained what it actually means.
yeah,
So for example, in this case, the N estimators. Okay,
yes,
for me, I went ahead and had to Google it and actually understand what that one was.
yeah,
In that case, in the kind of data we were using, but in
yes,
this case, all the other ones, the other parameters, haven't been explained. So I think it's okay, fine, not necessarily today that
yes,
we explain them, but they're important because we will at some point meet them.
yeah, you will need them.
And you need some basic knowledge about it. You don't need to really know it deeply, but just some basic knowledge what it means
Yes,
so that you can use it.
yeah,
So it was just a suggestion that I think we ought to know actually what they mean,
yes,
so that when you go to the next one, we'll know that in this case, even if we had a recording right now,
yeah,
you'll be like, oh, let me go back to that recording and actually really, listen to what it actually meant.
yeah,
It will actually help us. So, for example, the call sample, the subsample, and all that, for me, they're actually new. let me say the truth.
It's
And
okay.
I will really want to know what they actually mean.
Yeah, so for all the models that we've learned so far, so we will have a class on hyperparameter tuning, and that's when I'll explain what they mean. Because you've noted, so from all the notebooks that we've created in class, so for the majority of the models, I've included no hyperparameters. So it means that I'll have to go back and explain the parameters that we have for each and every model. So you can see, for example, for logistic regression, when I was fitting the model, so I included no hyperparameters. But for models like KNN and K-means, I explained what the hyperparameters were for those models. Yeah, but we will have a class for that. So Alex, so here you can see for logistic regression, I've not included any hyperparameters, but we will go back and I'll explain all the hyperparameters that we have for each and every model. Is that okay?
Absolutely, yes. Thank you.
Okay, great. So we'll have that. Yeah, so here we have our model instantiation. So we have xgb dot xgb regressor. So if it was a classification task, we will have xgb dot xgb classifier. Okay. Then we specify our objective. So remember here, I said that the objective is used to like determine what kind of model you want to fit. So for regression, we do reg, then we can use the squared error. Then we specify the other hyperparameters. So for example, the call sample by tree. So the call sample by tree is the percentage of features used per tree. Okay. Then learning rate, then max depth, then the alpha. So the alpha is the L1 regularization of leaf weights, then the number of estimators, so we can do the fitting. So after instantiating the model with the hyperparameters that we need, we go ahead and do the xgbreg.fit. After fitting, we get our predictions. Then after getting our predictions, we get our model score. So the model has an R2 score, so the R squared score of 0.19, and it has a root mean squared error of 1.035606. Okay, and this is our XGBoost model. So what we want to do here now is compare it with the other models. So the random forest regressor. So for the random forest regressor, we have, let's focus on the R squared score. It has an R squared score of 0.81. And this is a better performance than the XGBoost. So XGBoost has 0.19. Then next we can fit a linear regression model, which has an R squared score of 0.61. And from that, we can say that the XGBoost is actually performing worse than random forest and linear regression. So have you noted that? Because here we have an R squared score of 0.61. Here we have an R squared score of 0.81. So hope you've noted that. So we can say that XGBoost is performing worse than linear regression and random forest. So what can we do? So here I've just given an introduction as to what we can do. So we can use k-fold cross-validation. So k-fold cross-validation will be explained in the hyperparameter tuning class. And I think we can do that on Monday. Because today is on Thursday. So we'll do that on Monday. So what we do here is we create our parameters dictionary. Okay. Then what we do is we pass in our data matrix. So this is what we had created up here. So note now we are not using the X and Y. Then we specify our parameters. Then we specify our folds. So these, I'll explain these a little bit, but we will go into it deeper on Monday. So what k-fold does, this CV file that we are discussing over here, what it does is, let's say this is our data set now. Okay, so what it does is, here we've said, like, let's have something like the n folds. The n folds here, we have them as 3. So this is what we will have. So 3 folds. So this is fold number 1, this is fold number 2, this is fold number 3. Okay, so what we will have here is, this will be part 1 of our data set, this will be part 2 of our data set, and this will be part 3. So what we do here is, we will have model 1 using only this part of the data set. So that's model 1. So model 1 will use only that part of the data set to do the fitting. Okay, then model 2, then this is model 3. So model 2 will use only this part of the data set, and model 3 will use only this part of the data set. And after we've obtained our model results, so we will combine them and get their mean. Okay, and what we usually do is we check. So for example, this has 0.0, let's say 0.6, this has 0.7, this has 0.5 accuracy. So what we are checking here is, are these values differing by that much? So if they are, then it means that for each part of the dataset that we have here, we have different characteristics in between them. So that's basically what we are checking. So model 1 performance, model 2 performance, model 3 performance. And the models performance are being checked by these different subsets of the data. So this is subset data number 1, subset data number 2, subset data number 3. So for the first model that we've created, which has an accuracy of, let's say, 0.19, it has been fitted on the whole data set. So this whole data set was used, and it gave us an accuracy of 0.19. So when we do like a CV scoring with the number of folds, this is what we have. Like you can see the CV results.head. So we create a variable called CV results. We pass in our data matrix, pass in some variables in here, which I'll explain in that class. Then we get our CV results. So you can see for each CV that we are fitting, okay, we get a different score. So for the first dataset, we had an RMSE of 0.182. For the second one, 1.69. For the third one, 1.56. For the fourth one, 1.46. For the fifth one, 1.38. So you can see each has a different score. Then this is the last one that we had. So the last one that we had an accuracy of 0.59. Okay. Yep. So that's our result. So I'll explain this in detail on Monday. So our main aim was to like see how an XGBoost model works, but I'll explain the hyperparameter tuning part on Monday. Yep. Then you can go ahead and visualize the tree. So we train our model again. Then we use this part here to plot. So here we have matplotlib. So we create our figure. We specify the figure width and height. Then we plot our XGBoost. So using xgb.plot tree. So the same way we plotted a decision tree, we can plot a XGBoost tree. So we use the xgb.plot_tree method. We pass in our model and specify the number of trees. Then here we specify again the fig size. So this is what we have for our tree. Okay. Any questions on XGBoost? So I guess you will ask more questions on the hyperparameter tuning part on Monday, where we will be doing the K-fold cross validation and some other things. Yeah, but basically that's all for today. Yeah, yes, Bill.
Joseph,
Yes,
I have a question on the notes
yes,
just before the K-fold,
yes,
just before the K-fold cross validation using Xgboost.
yes, yes.
The immediate sentence, it reads, you can see that your RMSE for the price prediction came
Mm-hmm.
out to be around 1.208931 per $1,000.
Mm-hmm.
So, what is the main purpose of this root? We call it root mean square,
Root mean
something like
squared
that.
error.
Error.
Mm-hmm.
How? What's the main purpose of this root mean square?
So the main purpose is to explain like how much your prediction deviates from the actual values that we have. So let me try get a notebook here from one of the tasks I did. Maybe it's supposed to be on pipelines. Let me check. We have the loan.ipynb, topic3.ipynb. Let me open the two. So I'll share this with you also, so you can have a look at it. So you can see the RMSE was at 1079. So on average, our prediction of loan amounts deviate from the actual value by about 1079. So let's say you had an individual who had a loan amount of 10,000. So your predicted value is expected to, on average, deviate from these 10 by either plus or minus that. So that's what it means. So it means that your predicted value can be should not be a plus. So your predicted value can be 11,079, or it can be 8,920. So basically that's what the RMSE means. Okay. Is your question answered? So I had to use this example on a dataset that you can explain well on, because the California housing dataset is just a dataset that has been created for us, and the price is not that much. So you can see the price column has 4.526, so it's hard to explain what 4.526 means. But here, if we check the price column, you can see the loan amounts are in actual value. So for example, 10,000, 8,000, 15,600. So you can easily understand that. So that's basically what it means. And I guess the videos I shared in class explain it better. But do you understand it now better?
Yeah.
Okay. Then the R squared score is the variation that we have between the actual and the predicted value. So a higher value is better than a lower value. Okay. That's what we have. So I'll upload these. So this is from a freelancing task I did. So I'll upload it and you'll get to see what I did for this task, and you can learn something from it. So I've added some explanations here on EDA part and all that. This is part 2. So part 2 has been wrongly done, but I'm not the one who did it. So I'll not share this one because this one has been wrongly done. So this was a classification task, but the individual went ahead and fitted a regression task. Yeah. So let me upload the notebook, and then we should be done for today.